Hello, everybody. It's my pleasure to attend the conference today, and I would like to share some findings from our research. And we conducted research on characterization of the volatile compound in the model mu systems, and we use the GCMS as well as chemometrics approach to see how the ultrasound treatment and the fat content may affect on the production of volatile compounds in the sonicated mu system as a function of low frequency ultrasound. Next, please. And as we know that milk is highly nutritious, but it's also very susceptible to the processing treatment. And as a complex food system containing essential nutrients for human health, when we apply the heat treatment, like traditionally we used to apply heat treatment to the milk to produce the milk product. And when heat treatment has been applied on milk to produce that product to consumer and prolong the shelf life of milk, the severe heat treatment may cause some side effects, such as the denaturation and acceleration of proteins or the loss of some sensitive nutrients. And also, it may cause the undesirable color changes and of flavors. So, to avoid this problem, some non-thermal emerging technologies have been developed, and ultrasound is one of non-thermal methods which have been applied in dairy processing to improve the processing efficiency and product quality. And nowadays, ultrasound has been applied successful in fast separation, farming, or homogenization, or inactivation of enzymes and microbes. And we can see that we always we see like the milk the dairy industry already stable, and the technology quite developed well enough. But however, somehow when we have the yogurt product, we also see the it is separated in different layers. So with the application of ultrasound during the homogenization process of the yogurt product, it can improve the quality of product. So we can see if we apply ultrasound to the milk system, we can improve the processing efficiency and also improve the product quality. Next, please. So, what's the ultrasound treatment mean? Ultrasound can be seen as a technique using the sound wave which is higher than human hearing detection. The most common application of ultrasound in food and in dairy processing is focusing on how low frequency ultrasound at 20 to 25 kilohertz. And the main mechanism of ultrasound is based on a acoustic cavitation, and this is the phenomenon happening when the sound wave interact with the liquid, leading to the formation, the cloud, and the violent collapse of microbubbles in the liquid milk. And this will generate extremely high localized temperature and pressure. It will in turn cause the strong physical effects such as microaggressive forces, shockwave, turbulence, and it also may induce the formation of free radicals with initial lipid oxidation. Next, please. So, in the how the ultrasound effect on the milk system, we see that in the liquid milk protein and fat are two main components which contribute significantly to the physical and functional property of milk products. When milk protein and fat system is subjected to the ultrasound treatment, physical and chemical will lead to the denaturation of milk protein or the description of milk fat, and may also induce lipid oxidation. The side effect of milk, the damage of milk protein and fat to some extent may help to improve the functional property of milk products. However, one of the side effects may associated with ultrasound treatment is that it may generate some of flavor. As we know that the flavor is one of the most important indicator for product quality and determine the accessibility of consumer to milk products. The generation of flavor in sonicated milk may influence on the application of ultrasound in dairy processing. And because flavor and all flavor are attributed to the volatile compound. So understanding volatile profile is essential and necessary to reduce and eliminate the flavor insonicated milk. So this will help to promote the application of ultrasound in dairy processing and dairy industry later on. Next, please. So our research were conducted on the three model milk system, and for the first model milk system, this will be prepared with the whey protein 3.5% and fat at different concentration of 2, 4, and 6% respectively. And in model milk system, the second model of milk system, we repair 3.5% of casein instead of whey protein. And finally, we look at the model milk system containing the mixture of casein and whey protein with different ratio of casein to whey and fat at 4%. And then the ultrasound treatment was applied at low frequency and different processing time under controlled temperature of 10 degrees. And we use SPMC, GCMS, and also FTIR to extract and analyze volatile compound, analyze the changes of milk component regarding fatty acid and milk protein. Also, in addition to that, the pure fat system or pure whey protein and casein were also repaired for the comparison purpose and to investigate the origin of volatile compounds. Next, please. And we characterize the volatile compound in whey protein fat system and casein fat system as a function of low frequency ultrasound. So here are some volatile compound produced in whey F system. As we can see from the table, when we analyzing the volatile produced in whey F system, it's so that the volatile produce categorize a aldehydes, ketones, ester, alcohols, and hydrocarbons. Aldehyde and ketones are undesirable volatile compounds which are well known as secondary oxidative products. Most of volatile compounds were detected in both sonicated and untwisted samples. Beside that, the pure fat and pure whey protein system were also examined. The volatile compounds were produced in this system in different proportions, highlighting that most of volatiles were originated from fat portion than from protein fraction. Next, please. And we also try to relatively quantify the volatile compound in whey F systems. And as you know that GCMS is just semi-quantitative methods only. So here we just try to relatively quantify. And some typical volatiles are presented in the figures. It is obvious that 2-methyl-propanol are the most abundant compounds here, followed by hexanol and then heptanols, whereas nonanols and 2-nonanol were produced in very small amounts. 10 minutes of ultrasound produced the highest amount of 2-methyl-propanol and hexanol. So we can see, next please. In addition, we use principal component analysis to see the effect of whether ultrasound and fat content affected the production of volatiles. And as we can see in the figures that principal component 1 describes 96% the variability of the data set, and principal component 2 explains 2% of the variability. In figure A, samples sonicated for short time for 30 seconds and 1 minute are classified in the same group with untwisted samples in positive region of principal component 1. But the samples sonicated for higher time of 10 and 5 minutes are located in the other two different groups in the negative zones. This means that short sonication time has similar similar volatile production to the control, whereas the longer sonication time had different effects on the production of volatile compared to the control. So we can see that ultrasound did affect the production of volatile compound. However, the volatile produced were independent of fat content, as so in figure B we see here. The application of ultrasound for 30 seconds and 1 minute were therefore recommended to maintain the production of volatile compound similar to the untreated sample. Next, please. And we also investigate the production of volatiles in sonicated CF system. It means the system containing casein and fat. And similar to wave system, we see that volatile produced in CF systems were classified as aldehydes, ketones, ester, alcohols, and hydrocarbons. These volatile compounds were also detected in untreated samples, and the volatile compound produced in pure fat and pure casein in different proportion, with more volatile derived from fat than from casein. Next, please. And quantification of volatiles were also attempted. When we look at the picture, we can see that 2-methyl-propanol was the most abundant volatile compounds, and followed by pentanol and hexanol. However, 2-nonanol and nonanol were produced in smaller amount. Ultrasound twisted sample for 10 minutes produced the highest amount of 2-methyl-propanol, heptanol, and hexanol. Next, please. And here is the principal component analysis I applied in the case of CF system. And we can see that principal component analysis were also attempted and investigate whether fat content and ultrasound affected the production of volatile. And compared to the waste system, within principal component 2 here, we cannot see the clear distinguish. So then it was gone to BC3, principal component 3. It's obvious that short and high sonication time have different effect on the production of volatile. And we can see here 3 distinguished groups in figure C and D, labeled by ultrasound time. Samples sonicated for 30 seconds and 1 minute were classified in the same group with the control. 5 and 10 minutes sonicated samples were distributed in other 2 different groups in negative zone of principal component 1. It means that short sonication time has similar production of volatile to the untwisted sample, and whereas longer sonication time had different effect on the volatile production compared to the control. So it's suggested that the use of ultrasound for short time is recommended to minimize the production of volatile compound closer to the untwisted sample. Moreover, the principal component score plot according to fat content, so that production of volatile were independent of fat content. So we can see here with the application, with the use of GCMS and in combination with principal component analysis, we can have the visualize view about to understand the general effect of ultrasound as well as the fat content on the production of volatile in sonicated sample. Next, please. Besides characterize the production of volatile compound in sonicated system, we also analyze the corresponding changes in the milk component reacting fatty acid and reacting fatty acids and milk protein. And here is the analyzing of the changes in milk fat structure by using FTIR. And we can see that when we use FTIR, the sample level by fat content were distributed into distinguished groups. Samples in the same group share similar characteristics, were different from the other groups, and visible components called plot therefore show that fat content had effect on the milk protein and fat, whereas the effects of ultrasound were not clear. And next please. Next please. And therefore, the further access to specific bank associated with fatty acids in fat and ester group in fat or fat protein complexes, so that ultrasound call the changes in the intensity of fatty chains in milk fat and the increase of lipid protein interaction. This may be related to the description of fat global and the concurrent association of milk protein and milk fat. Moreover, there were changes occur in secondary structure of milk protein, and we can see in the figure C. And we see that the random coils were increased with sonication time. At the same time, beta seed and beta turn alpha helix were changes in their intensities. And this is the secondary structure of milk protein developed by anti. Next, please. And this is similarly, we apply principal component analysis to analyze the changes in secondary structure of casein in CF system. And we also see that fat content affect the milk protein and fats, whereas the effect of ultrasound treatment were not clear in this situation when we use principal component analysis to analyze the data here. Next, please. We can conclude for the VF and CF system that fat content affected the intensity of milk fat and fat protein complexes in both VF and CF model milk system. And when we prolong the sonication, we can see it had the effect on the intensity of milk fat in VF and CF system, and the intensity of ester group corresponded to milk fat and complexes of fat and protein increase with the increase of insonication time in both VF and CF system. And also we see that the secondary structure of milk protein changes as the function of sonication when we use FTIR to analyze the protein structure. Next, please. So we see this is the general conclusion for VF and CF systems. Next, please. So after we look at the VF and CF system, we also have a look at the mixture of whey protein, casein, and fat system. And we also have that the volatile compound detected were categorized in different groups such as aldehyde, ketone, ester, alcohol, and hydrocarbons. Similar volatile profile were detected in sonicated and unsonicated CF system. However, we see that the concentration of some aldehydes and ketones increase with the sonication time. It means that sonication had the effect on the production of volatile compound in the model milk system containing mixture of whey protein, casein, and fat. Next, please. And here we also see among these compounds, 2-methylpropanol are the most abundant, followed by pentanol, hexanol, and 2-methylpropanol and hexanol were the highest in 10 minutes sonicated sample. Non-nano were generated with a smallest amount. Next, please. And here we apply principal component analysis on the for the samples, and we see that so from the figures, samples were distributed into 3 different groups according to sonication time, and samples sonicated for 1 minute were grouped together and located closer to the control in the positive region of BC1 compared to 10 minutes sonicated sample. However, figure B shows that the production of volatile were independent of ratio of casein to weight. Next, please. We also apply FTIR to analyze the changes in secondary structural of milk protein in YCF system, and we see that there was significant increase in random coils intensity of random coils and concomitant changes of alpha helix and beta sheet and beta turn with the sonication time. Next, please. And we can see here are the example of the changes of milk fat in YCF system. The intensity of fatty acid chains in fat and ester group in fat and fat protein complexes increase with sonication time and higher than the control. The description of fat global and interaction of fat protein suggested that milk protein denature as the function of ultrasound. Next, please. So after investigate the production of volatile compound in the mixture of whey protein, casein, and fat system, and also the corresponding changes of milk fat and milk protein, we can see that aldehydes, ketones, and ethos acetate and hydrocarbons were detected in sonicated YCF system. Time of sonication affected the production of volatile compound, whereas the volatile production was independent to ratio of casein to whey. And also we see that secondary structures of milk protein were affected by sonication time and irrespective to the ratio of casein to whey. Fatty acid chains and ester group associated to fat and fat lipid protein complexes were significantly affected by sonication time regardless of ratio of casein to whey. Next, please. And we can see that when we apply GCMS in the combination of principal component analysis, can give us the general picture of how different factors can affect on the production of volatile compound and on the corresponding changes of milk components. So we can apply this one in the Pacific milk product with the combination of ultrasound in the processing to improve the quality of milk product and also improve the processing efficiency to promote the application of ultrasound in the dairy processing later in the future. Thank you.